Hi and welcome to the second episode in my series on quantum field theory. In this episode, we embark on an expedition to unveil the propagator of our quantum field in four-dimensional spacetime. This elusive quantity holds the key to understanding how the field at one point in spacetime influences the behavior of the field at another. While we will delve into the mathematical underpinnings of the propagator in this video, in the next video we will look at it from up close to get an intuitive idea of what the propagator actually tells us. Before we start, however, let's revisit what we spoke about in the previous video. In the previous video we laid the groundwork for working out a quantum field theory in the realm of zero dimensions. We have seen that if we start with a zero-dimensional random variable phi, we can only study its probability density closely, and we do this using Green's functions. We then added a source term j, which led us to the definition of a path integral. From this path integral, we derived the Schwinger-Dyson equation, a powerful tool that governs the behavior of our quantum field. This equation revealed the connection between the expectation value of our random quantum field phi in the presence of a source term. We then advanced to one spatial dimension, filled in the free action into our Schwinger-Dyson equation, and obtained the following formula for our field expectation value at location n as a function of the field expectation values at location n plus 1 and n minus 1. This is where I want to continue to derive the propagator. Our quest starts with the Schwinger-Dyson equation for a free field in one spatial dimension. So how should we begin to solve it? Whenever there is an infinite set of objects with some relation between them, it is always a good idea to use generating functions. Since our field phi n is a function of the infinite set of sources j, it makes sense to write phi n as a sum over all these sources jk, each matched with what we will call the propagator capital Pi sub nk. We also divide by h bar to fix the units. Now consider the field phi n. Since there is no difference between the type of fields left and right of phi n, we classify the theory as parity invariant. This inherent balance also echoes through the action, ensuring that the theory's essence remains unchanged if we reverse all spatial coordinates. In the realm of shifting labels, we saw before that we can translate our labels by any desired amount, a feature that grants our theory translation invariance. These two invariants, parity and translation, impose a strict code on our propagator, demanding that it remain immune to their respective manipulations. As a result, the propagator's essence can only really be defined by the absolute distance between its two partners n and k. We shall therefore write it as capital Pi of n minus k. Now, observe what happens if we replace each phi in our free Schwinger-Dyson equation with this new expression. We get an equation with an infinite number of j's inside. Since this equation must hold true for any value of j, we can isolate j equals j0, revealing a familiar looking relationship between the propagators. You might find that this equation looks strikingly similar to our free Schwinger-Dyson equation, but the seemingly insignificant addition of the delta function makes all the difference in solving this equation. The trick is to employ a Fourier transform to shift our variable n to its conjugate counterpart z. We therefore write r of z equals the sum over all n of the propagator, which is a function of n, times e to the minus I n z. This is our second time using generating functions in this video. We can reverse this expression, rewriting the propagator as a function of r of z in this way. This is exactly the magic of a Fourier transform, and if you are interested, you can try to prove that this expression has to be true given our definition of r of z. We now insert the propagator integral into our equation, replacing the delta function with its own Fourier transformed equivalent. Since we find ourselves with an integral on both the left and the right hand side of this equation, we can conclude that the integrands also have to be the same, yielding the following equation for r of z. We can then rewrite this expression to reveal the true form of r of z. Using that e to the iz plus e to the minus iz is the same as 2 times the cosine of z, the exponentials vanish from our denominator, and we get an even cleaner expression. Since we previously wrote the propagator as an integral over r of z, we can use this expression to derive the expression for our propagator Pi of n, which now writes as the following. So far we employed generating functions twice to unveil this very neat expression for the propagator, the object that bridges the gap between distant points in our one-dimensional tapestry. Though the intricate details remain hidden for now, it is at least interesting to see what the propagator looks like when the integral is solved. Solving the integral reveals this very simple function, which is an exponential of the absolute value of n. As the absolute value of n increases, the propagator's influence diminishes, mirroring our intuition that distant fields exert a diminishing impact on our field at location 0. Closer fields, however, exert a growing influence, respecting the local nature of our theory. This particular solution only takes form when mu is bigger than 2 times gamma, which is a restriction that we will find ourselves abiding to a little later in this video as well. If we wouldn't follow this restriction, we would get poles in our integral, resulting in solutions on the complex unit circle, which do not evoke a simple physical interpretation. Now that we have our definition of the propagator in one spatial dimension, let us clear up the connection between the discrete set of quantum fields and the observable world. To achieve this, we shrink the distances between our zero-dimensional quantum fields to infinitesimally small magnitudes, represented by the tiny unit delta. In this regard, we rewrite our position as x equals n times delta. We can thus replace all n's in our equation of the propagator with x over delta. Now, since the exponential ought to be unitless, let us also rewrite z as k times delta. Replacing z with k times delta and replacing the integrand dz with dk times delta, we obtain the following. As we integrate from minus pi over delta to plus pi over delta, we witness the propagator embracing the infinite expanse of the physical continuum. We then approximate the cosine in our denominator with 1 minus k squared delta squared over 2. And by this last step we nearly arrive at the goal of our quest. In order for our propagator not to depend on this infinitesimal delta, we need to find a way to remove this delta dependence from our expression. To achieve this, let us redefine the characters mu and gamma in such a way that the denominator in our integrand is linear in delta, such that it cancels the delta in front of the integral. A quick solution would be to set gamma equal to 1 over delta, and then mu proceeds to be 2 over delta. However, by rule of the restriction we have seen before, we need mu to be strictly greater than 2 times gamma, so why don't we add a term m squared over 2 times delta to mu? And while we're at it, I'll also subtract m squared over 4 times delta from gamma. The reason for this is that it creates a simpler action later on, and we are free to do so why not? M is of course just another constant, which we will take to be real and positive, because I guess you already know what it stands for. With our redefined mu and gamma in place, we finally obtain the propagator equation in one spatial dimension. This is a great result in and of itself, and we can solve the integral to get a propagator of h bar over 2m times the exponential of minus m times the absolute value of x. This result mirrors our counterpart from the discrete case, but now we turn our labeling into a continuous one-dimensional line representing the x-axis in units of length. As we venture from the discrete realm of quantum fields to the continuous one-dimensional line, we must also transform our action, which is the cornerstone of our theoretical framework. The so-called while ordering instructs us to express phi of x as 1/2 times phi n plus 1, and the derivative of phi with respect to x should then be defined as 1 over delta times phi n plus 1 minus phi n. Using our previously obtained expressions for mu and gamma as a function of this delta, we find that the action is updated to the following result. If we now choose to redefine our source term j such that jn equals delta times jx, we can take the delta out in front, and we can now replace our sum with an integral over x. Thus, we obtain an action that is an integral over x of our field derivatives and sources, which are all functions of x itself. As promised, I want to end this video by upgrading the propagator from 1 dimension to the 4 dimensions of spacetime. The steps are very similar to what we have done up till now, so I will only present a summary of how it's done. Let's start by adding 3 dimensions to our 1-dimensional discrete action from before. We do this by writing our field phi n as phi a vector n, where vector denotes a 4-dimensional array of numbers n0, n1, n2 and n3. Here n0 will denote the time dimension and ni denote the spatial dimensions. Just as in the 1-dimensional case, we introduce interaction terms between neighboring fields, and we make a distinction between temporal and spatial interactions by giving the temporal interactions a coupling constant of gamma 0, and for the 3 spatial interactions we simply use the same gamma again. Note that if I write vector n plus 0, I mean the same vector n, but where the 0th component of n gains a plus 1. The same for vector n plus 1, 2 or 3. If we enter this action into the Schwinger-Dyson equation and rewrite our field in terms of propagators, we get the following expression. Embracing the Fourier transform, we conjure up an expression for r of z, where z is now also a 4-dimensional array of numbers, and if we fill this into the equation of our propagator, we get a familiar integral expression again. The last step is to redefine mu and gamma in a sensible way like such. I will leave it as an exercise for you to follow all of these steps and prove that it results in our final expression for the propagator of a quantum field in 4-dimensional spacetime. Congratulations to those who have reached the end of this video. We've delved into the depths of mathematical concepts, but if you weren't able to follow all of these steps in this video, don't worry. As a takeaway for you, I just want you to realize that the philosophical essence of our pursuit remains remarkably straightforward. We began with a single random number phi, which we associated to a 0-dimensional point, an infinitesimally tiny universe, and we sought to uncover its probability distribution as a measure of its uncertainty. As we introduced more of these 0-dimensional points, each described by their own probability distribution, we wove them together into a network of interconnected random variables. If you imagine the random variable at location 0 to suddenly become exceptionally high, the variables at location 1 and -1 will feel this event and will increase in response. Like a ripple in a pond, the explosion is carried out towards infinity. This interplay between the points is described by the propagator. We can arrange these points in a 1-dimensional line, but of course we can extend this to any desired dimension, which is what we did for 4 dimensions in the end. Next time, as promised, we will study the propagator and the source function in particular in more detail, so I hope to see you then. For now, thanks for watching.